deposition. Something about the surface tension forces of the Pugno and perhaps adhesion to the surface triggered collapse. So those are really interesting questions that we couldn't really discriminate. So Tomek Kovalevsky was our collaborator on the AFM, and he used an erosion technique. Those of you who might be expert, there's a way of backing out the structure of nanostructures through this mathematical algorithm where we could assume an elliptical shape. So even in the region where it wasn't fully collapsed, such as up here, it was deformed into an ellipse, and not a perfect cylinder. And then in the regions where it's collapsed, in a moment I'll show you a profile. Maybe I can jump ahead. Yeah. What happens is it collapses fully. And so actually just the height here almost immediately tells you the number of walls that you have, the number of nested, what would have been cylinders before collapse. And we have these bold regions here. So the energetics analysis is really quite straightforward. You're taking a cylinder and deforming it elastically. And so there's an energy penalty for creating these relatively high radius of curvature holes. But there's favorable adhesion occurring here where the innermost cylinder has collapsed onto itself, and then a larger surface of interaction with the substrate, such as silicon dioxide. So the surface energies need to be accounted for. The energy to deform the tube needs to be accounted for. And then when you add those up, you can consider that the tube might be stable or metastable to collapse, depending on the overall diameter and the number of shells, either in free space or when contacting the substrate, if you somehow knew the adhesion energy to that particular substrate. And so with this method of constraining the perimeter and our knowledge of the thickness, we could unequivocally show that this was a three-walled tube of a particular diameter if it were not collapsed. And so the surface energetics that we worked out here, this is a lot of reading, but I've just told you to calculate that bulk is this statement here, 5 times the stiffness divided by radius of curvature. And then we have this adhesion that I told you about here. And we calculated for this particular three-wall tube that it actually was not stable to collapse without the adhesion to the SiO2. So by using values for surface energy for graphite and for silicon dioxide, and adding those together, we came up with an adhesion energy per area that was fairly close to what we calculated was needed to make the overall energetics or energy negative. So probably in this particular case, it was contact with the surface that critically helped to drive the collapse and hold it in the collapsed position with difficulty. Of course, we can unequivocally say that. Then another thing we found was a collapsed and twisted section. And this was kind of interesting because, not surprisingly, if you think of something like maybe an inner tube is not the best example, but as you go toward this conformation, it's going to be very compliant out of plane. The persistence length of a ribbon along the ribbon, such as one of these collapsed nanotubes, is much, much shorter than the persistence length of a nanotube that's not collapsed. So single wall carbon nanotubes can have persistence length for coaxing calculations of 20 microns. And persistence length along a ribbon might just be a few nanotubes. So we found that the structure was significantly more rigid when we were capping in this configuration, and then it twisted, it came down flat, and it was significantly more compliant. Let me visit another set of ribbons that have been found in a separate sample. this was collaboration with Mark Dyer. Then Min Fung moved on to work at Zyrex for a while before moving to the University of Illinois. So he found other ribbons, again dispersing to Pugno, and you can see the way these contacting surface can drape over other structures in the surface of the nanotubes. And this is one of the more beautiful images. I really like this image because you can see it perfectly follows the underlying nanotube. It shows how remarkably compliant it is. And so every year or so I check in with my synthetic colleagues around the world and say, I ask, is anyone making high concentrations or high yields of ribbons? Because the implications for processing in terms of composites are very exciting. You know, the ability to get these ribbons to line up through shear processing compared to nanotubes that are now collapsed is very, very interesting. But it seems that they're difficult to synthesize, and they're usually only present in very small percentages in samples which are otherwise only more standard nanotubes and not collapsed. This is the same picture again in terms of treating the energetics, and what happened here is Min Fung found 8 of these ribbons. 6 of them were stable to collapse even if they were not adhered to the surface. 2 of them, from calculations, were stable to collapse once we accounted for the adhesion to the surface. So this is a long discussion, but the energetics are very similar to what we just talked about. I'm going to go through this rather quickly so we can get to discussing shell sliding. This is just showing that you can actually get the number of nested shells by pounding on the nanotubes and accounting for the Hertzian force. And you can actually back out from the images the number of shells in different regions in a nanotube that's bent and kinked like this. So it turns out in this region 2, it's actually a smaller number of shells than region 1. Okay, now we're going to talk about interlayer registry. And we have a really fascinating object that I'll show you momentarily that Min Fung found now doing transmission electron microscopy. So again, he's finding ribbons, but this time it had a twist. Well, a twist is not that big a deal if it's clamped on both ends, like here. And so this is a lacy carbon support film, and it's clamped here and it's clamped there, and it happens to have a twist in it, so that might have happened during deposition in terms of how the solvent front might have pushed across this nanotube when it was drying. But this is a very puzzling situation. We've got a twisted ribbon which is extending into free space and not clamped on this end. So that shouldn't be, if it were a twisted beam and it was elastic, it would simply relax backwards. It's not clamped. So why is that happening? And to make a long story short, Min Fung invented this hypothesis that it probably had to do with the interlayer registry. And so if you take an armchair tube and collapse it, you end up in the 2 regions that are contacting each other with AB stacking, the most favorable energetic stacking. If you take a zigzag tube and collapse it, you end up with AA, the most unfavorable. And coincidentally, Vin Crespi, for treating this issue of shell sliding, had just done ab initio calculations where he calculated with his team 12 millielectron volt difference between AB and AA per atom pair on the neighboring layers. And so there was already a ready-made model in terms of the energetics for us to consider. So the hypothesis was that this is one of those sorts of tubes that, by twisting, can achieve a better interlayer registry in the collapsed inner shell than if it were not twisted. And that's pretty much where we stopped. I mean, we mapped out the number of layers and so on, but we couldn't really prove that hypothesis. It just seemed to be sensible. So this is a description of how the ribbon might have twisted and why could there conceivably be this this static twist, okay, in a freestanding ribbon. And so we said it could actually be the interlayer interactions. So in many cases, you can ignore the interlayer interactions and just smear it out and assume that the atoms are not there. You don't have to worry about atomistics in a sense. But in this particular case, we're saying that it's actually critically important for the overall structure that's observed. So when Min-Fung moved to the University of Illinois, he collaborated with Young Huang. You may know him, he's now moved to Northwestern. And they treated this issue of commensurance or incommensurance, or the degree of commensurance, where highly commensurate might be AB stacking, and highly incommensurate would be off AB stacking. And is there a driving force, for example, for creating twists? This is showing a set of different armchair tubes from small diameter. Then you have metastable to collapse when you get up to a 30-30. And then in this regime, above 3 nanometers in diameter, it's actually stable to collapse in terms of treating the energetics that we talked about. So in that collapsed state, what would happen to an armchair tube? Let me jump ahead here. So for example, a 4 nanometer diameter armchair tube, when it collapses and makes an AB stacking, it's perfectly happy. There's no reason for it to try to shift in 2 layers relatively, such as by twisting. It's already in the energetic minimum. In contrast, a similar diameter zigzag tube is energetically unfavorable and probably would have a relatively large driving force for sliding 2 layers with respect to each other and generating a shift, a twist, excuse me. So this is showing their calculations using, again, that bin Crespi potential, 12 MeV versus 0 MeV, everything in between, for armchair and then slightly off armchair all the way out to zigzag. And if you look at the zigzag tube, you can actually see that it's bulged outward here and in the opposite direction here. And you actually have that if you were walking along a twist. Okay? And here we're seeing the moire patterns where, of course, with armchair we have just the AB stacking. And then for these other sorts of configurations, you have other sorts of patterns in terms of the interlayer registry. They then developed this sort of color-coded mapping in terms of this angle alpha for rationalizing what the interlayer registry was, and therefore the driving force for twisting. You can see that even though a large number of the tubes are not stable to twisting compared to the armchair energy, there's a significant sort of distance that they have to go to get over the barrier, so they may not twist significantly as a result. So I think that that paper was very nice in terms of extending that hypothesis that we had but not really proven, to demonstrate that this is a real effect and it can drive twisting in these sorts of structures. And they speculated about the importance for CNT bearings, types of structures where you might have nearly frictionless shuttles, for example, such as Paolo referred to. Well, the twist paper actually came later than this paper. So this was an example where we were able to extend our experiments because, as I mentioned, when we broke the outer shell, sometimes the lower cantilever was not so strongly deflected. In other words, it was a weak outer shell because of this pig, that it didn't snap back very far. And so fracture had occurred in the outer shell, and we ended up with separated fragments, but they had not pulled out all the way like a sword and sheet. They were still connected. And so we decided we might as well do shell sliding experiments on a couple of those, since it's an interesting situation. It's not an ideal situation in some sense because we don't know at SEM imaging and resolution what the fracture edge looks like, or the periphery of one tube versus the other. It could be very jagged and so on. So in terms of treating with a simple force model that we worked on with Boris and Oates, in addition to a surface tension or a line tension at the periphery, there's this issue of perhaps dangling bonds or bonds that are dragging along the tube. And we buried all that into one term to see what the gamma value looked like in terms of fitting energetics. So this is showing that we have these break is curved, but we still have the outer shell connected to the inner shell. We have a long distance to go to pull it out, and then it collapses onto itself and twists and so on. And these have so many nested shells that it's still quite rigid, not prone to collapse. And so as we plot the position changes of the cantilever tip versus time, we video recorded the experiments, we end up with stick-slip behavior that can be mapped in terms of a shear strength and a contribution in terms of this edge effect. And so we ended up with two different responses in a sense. One tube had a force versus contact length between the outer shell and the inner shell, which was sort of sensible in terms of the range of shear strength values for graphite that ranged from about 0.2 to 0.7 megapascal. And this value was around 0.5. But the other multimodal carbon nanotube had almost smooth pull-out once we overcame the stick and the slip started. And it had a fit value for the shear strength of about 0.08 megapascal. And this caused us to conjecture about the possibility of frictionless sliding. It's now going to be visited by other people as well. And so indeed, there have been models done where they have highly idealized tubes with not these raggedy edges and so on. They could end up with certain choices of NM for the outer shell and NM for the inner shell with remarkably low values further model of friction for sliding. And there is, an effect that I'll demonstrate with C60 being sucked into a nanotube that has to do with this edge effect or line edge. So I'll wrap things up by quickly referring to some aspects of the study with Dongjian and Lingjun Lu of placing a C60 at the edge of a carbon nanotube of different types, such as a 1010 or a 99 or even smaller ones. Now we know that the 1010 inner diameter of 7 nanometers is a very nice fit for the 7 nanometer diameter buckball. So we expected to see that it could move back and forth. So this is the configuration that we're looking at, and in this simulation, we typically started the buckyball at the end of the nanotube and outside the nanotube, and it would be drawn in through the surface tension interaction. And I'll jump over. Well, we used a couple of different potentials, and I'll skip that. It's pretty straightforward. We used Leonard-Jones at large distances, and we used LDA at short distances. It's well known that the inverse 12 dependence is much too stiff, it's too rigid compared to more appropriate potentials at short interatomic distances. So we essentially splined those together. And the LDA comes from David Tomanek, and it was compared to full ab initio calculations by Butker that mapped out the equation of state of graphite as a function of pressure. And so this shows that what happens when you have a C60 on the outside of the tube is it gets sucked in just like a straw, and then it zips back and forth. So what's happening is it goes out the other end, actually projects out the other end, and then gets sucked back in, and that goes back and forth for a very long time. Actually, you can't typically calculate calculate for a 10-10 tube of the length that Dong chose when it actually stops, because the calculation would run for too long. And then there were some other studies that were done on smaller diameter tubes, and so I won't delve into those. It was possible to project the C60 into the 9-9 tube, which is a little bit undersized, and then the tube actually had to expand a bit, and the C60 would slow down, of course, more rapidly than inside of a 10-10 tube. But I think this sort of captures the idea of something like a shuttle, a nanotube against a nanotube, or a C60 on the outside of a nanotube. And it is of interest that one way of making the p-pod structures that David Woodsy's group made first was through holes being present in single-wall carbon nanotubes on the sidewall. And the C60s would surface diffuse and then get sucked in again through the surface tension effect and fill the tube up with these p-pod structures that provided beautiful TEM images. And then people began to put the endothelial fluorines inside. It was a very nice way of having a stable environment to image the metal at very high resolution versus having a C60 on another sort of imperfect surface. So this ties in with what we talked about in terms of interatomic registry and shell sliding in tubes, but also the displays for misoriented graphene against graphene and how that might have very low friction. Are there any questions about this one?
Published a paper on Nanomechanics results, treating something that has been observed experimentally. It is a case of a bundle, nanotube bundle, with set collapse of nanotube inside. It's something similar to what you
Completely collapsed or
fast? Some of them are completely collapsed, but without, of course, external pressure, just due to surface tension. And this is important because if you have collapsed nanotubes, you can increase the strength, of course, against sliding failure. And I think this
because there's a much larger surface.
Exactly.
Yeah. Definitely so.
But there was an instability, not a metastable transition as you have observed. Kind of really a bug. Because you mentioned some metastable or not.
Well, as you made larger, as one would make larger and larger diameter tubes, even though it might be possible in a computer to configure things so that you have the infinite crystal when you develop this facet. To me, it seems very prone at some diameter to be likely to collapse along a given direction due to slight perturbations. Now, I think the ribbons would be really wonderful if people could just figure out how to synthesize them and find yield.
Another question. According to my understanding, for the problem of the pull-out of the internal wall of the nanotubes, I think that at the beginning you have, you can confirm this, at the beginning, if the overlapping length is very small, you have a stress-based failure. So in that case, you can define a shear strength. If the overlapping is very small, okay? But if the overlapping it becomes very large, you have another mechanism that is an energy-based effect, fraction mechanics. So in that case, if you...
In this case, the friction is very, very small. Between two tubes, the inner tube and the outer tube, the shear force is extremely small. So that lends the huge, probably very difficult to reach that length. Because it's very weak, very weak.
But if you apply fraction mechanics concept, you have At the end, you have a nearly constant force that is all they observe. Yes, but if you put the different surface energy, you get some values for the force, the plateau.
Yes.
This is a plateau. It is comparable to what you observe.
And where the shear strength is not high.
The shear strength cannot be defined because otherwise you have to admit a huge size effect of the shear strength, because the shear strength will tend to zero increasing the development length because it is not based on stress.
There's
This
a
is my
recent,
understanding.
there's a recent paper from a Japanese group that I didn't include in the talk, where they state for the idealized case, we don't have a raggedy edge. For certain choices in N that the shear strength is not relevant. And it's just this edge based
Yes.
effect that matters.
Fraction mechanics means basically the edge.
So that's
For large developing length.
So it is a criticism of our
No, that is false. I remember this paper.
It's the problem being first. We probably should have been